Something terrifying is happening at Yosemite Park.
There were two massive rock slides this week at El Capitan, the formation in Yosemite National Park that draws hikers and climbers from around the world.
Tonight, a look inside the intense fight to save the treasured sequoias of Yosemite National Park. Hot and dry conditions making it difficult for crews to put the fire down.
Tensions are rising as after a series of catastrophic incidents that left everyone in shock, officials issued a tragic alert and closed off popular areas. Join us as we reveal the terrifying reason behind horrible events in Yosemite Park. But before we delve into that, an overview of this area is needed. Yosemite National Park, as we know, is located within the heart of the Sierra Nevada, the largest fault block mountain range in the United States. Trending northwest-southeast for more than 300 miles, the Sierra Nevada traverses half the length of California, with the Central Valley to the west and the Basin and Range Province to the east. It is an asymmetric mountain range with a long, gentle western slope and a short, steep eastern escarpment. It is 50 to 80 miles wide and extends in elevation from near sea level along its western edge to more than 13,000 feet along the crest in the Yosemite area, and more than 14,000 feet along the crest in Sequoia and Kings Canyon National Parks. The highest peak in the Sierra Nevada and in the continental United States is 14,505-foot-tall Mount Whitney in Sequoia National Park. Mount Lyell, the highest peak in Yosemite National Park, rises 13,114 feet above sea level. Geologically, the Sierra Nevada is a huge block of the Earth's crust that is bounded on its east side by a fault system, along which the Sierra has been uplifted and tilted westward. This combination of uplift and tilt, which is the underlying geologic process that created the present range, is still occurring today. The geologic story of Yosemite National Park can be considered in two parts. First was emplacement of granitic rocks in a subduction zone and metamorphism of older sedimentary rocks. Later came uplift, erosion, and glaciation of the rocks to form today's mountainous landscape. The Sierra Nevada is mainly composed of granite, a salt and pepper appearing rock composed primarily of quartz, plagioclase, potassium feldspar, biotite, and hornblende. Granite, granodiorite, diorite, and tonalite are all forms of plutonic rock that occur in Yosemite and are loosely referred to as granitic rocks. The many varieties of plutonic rocks in Yosemite and the rest of the Sierra are due to different compositions of magma intruded into Earth's crust at different times, and separation of intruded magma into crystal-rich and crystal-poor fractions. The differences are visible in color, grain size, texture, structure, and mineralogy, and in response to weathering and erosion of the rocks. The granites of Yosemite are part of the Sierra Nevada batholith, a large amalgamation of plutons. Plutons are bodies of molten rock material, magma, that froze within the Earth, rather than erupting to form volcanic rocks. The batholith formed due to subduction, where tectonic plates converge and one dives under the other. Around 220 million years ago, the ancestors of the Pacific Plate began to subduct. Beneath the North American Plate and the west coast of California was similar to today's Andes of South America. The majority of granites in Yosemite National Park formed during the Cretaceous period, between 105 and 85 million years old. They were eventually exposed on the surface by gradual erosion of the overlying rocks over millions of years. The huge amount of eroded sediment was transported westward by river systems into California's Central Valley. Evolution of the landscape is as much a part of the geologic story as the rocks themselves, and Yosemite is a place where the dynamism of geologic processes is well displayed. By the end of Cretaceous time, about 65 million years ago, subduction and granite production ended. At that time, the Sierra Nevada was a substantial mountain range. For tens of millions of years, gradual erosion stripped away the overlying volcanic and metamorphic rocks, exposing the granites that once formed at depth. Within the past 20 million years or so, the region began to uplift and tilt toward the southwest, a process that would eventually lead to the present Sierra Nevada. As the rate and degree of southwest tilt increased, the gradients of streams flowing southwestward to California's Central Valley also increased, and the faster-flowing streams cut deeper and deeper canyons into the mountain block. In short, Yosemite National Park records its dynamic geologic history in its rocks and landscape, being a key place to understand the evolution of Sierra Nevada and geological processes such as granite formation, glacial geomorphology, and tectonics. The Yosemite and the southern Yosemite region are home to several Native American cultures, including the Sierra Mono, Southern Sierra Miwok, Chukchansi, Yokut, and Ahwanichi tribes. Each of these cultures has a rich history and unique traditions that have shaped their way of life for centuries and shaped much of the region as well. Archaeological discoveries confirm human presence in the Sierra Nevada region for 12,000 years, with indigenous communities inhabiting Yosemite for at least 4,000 years. Yosemite Valley, rich in cultural history, was inhabited by the Ahwanichis, named after Ahwani, meaning gaping mouth. The 19th century gold rush brought European settlers, leading to the Mariposa Indian War and severe hardships for the native tribes. Many indigenous people were killed, succumbed to diseases, or were forced to leave their ancestral lands. In the years that followed, a few Ahwanichi and Miwok people did manage to return to their homeland. However, over the 20th century, the number of native people residing in Yosemite Valley declined. The older Indian village was disbanded in the early 1930s and replaced with cabins. Over the coming decades, the National Park Service slowly removed the housing. The last homes were razed in 1969. The earliest records of seismic activity in the Yosemite area are largely anecdotal, as systematic seismic monitoring in California did not begin until the late 19th century. However, indigenous peoples of the region, such as the Ahwanichi, undoubtedly experienced and were aware of earthquakes long before European settlers arrived. The first documented significant earthquake in the Yosemite region occurred in 1872. This earthquake, known as the Owens Valley earthquake, had an estimated magnitude of 7.4 to 7.9 and caused significant damage in the Owens Valley, east of Yosemite. Although the epicenter was far from Yosemite, the quake was felt throughout the Sierra Nevada, highlighting the interconnected nature of tectonic activity in the region. The 20th century saw more systematic monitoring and recording of earthquakes in and around Yosemite National Park. One of the most notable events was the 1933 Long Valley earthquake, with a magnitude of 6.3. The epicenter was near the town of Mammoth Lakes, east of Yosemite. This quake caused rockfalls and landslides within the park, reminding visitors and geologists alike of the ever-present seismic risks. Another significant event was the 1980 Mammoth Lakes earthquake sequence. This series of earthquakes, including several with magnitudes above 6.0, caused widespread concern about the possibility of a volcanic eruption in the Long Valley caldera. Although the epicenters were outside the park boundaries, the seismic activity was felt in Yosemite and prompted increased scientific scrutiny of the region's seismic and volcanic hazards. While large earthquakes are relatively rare in Yosemite itself, smaller quakes and their associated seismic activity have had a noticeable impact on the park's landscape. Rockfalls, a common and dramatic occurrence in Yosemite, are often triggered by seismic activity, weathering, and freeze-thaw cycles. One of the most significant rockfalls in recent history occurred in 1996, when over 80,000 cubic meters of granite fell from the Glacier Point area, resulting in one fatality and several injuries. While the exact trigger for this rockfall is uncertain, it highlights the inherent instability of Yosemite's granite cliffs, which can be exacerbated by even minor seismic activity. The year 2024 witnessed a torrent of quakes around Yosemite region. According to statistics, as of July 31st, Yosemite Valley has had 528 quakes of magnitudes up to 3.8 within up to 63-mile distance, in which there are 7 quakes above magnitude 3, 69 quakes between magnitude 2 and 3, and 452 quakes below magnitude 2 that people normally don't feel. The increasing number of earthquakes in the Yosemite region is a testament to the dynamic geological forces that continue to shape this remarkable landscape. While large earthquakes are relatively rare, the seismic activity in the region underscores the importance of ongoing research, monitoring, and preparedness. By understanding the seismic history and potential risks, we can better appreciate the complex and ever-changing nature of Yosemite's stunning environment and take steps to ensure the safety of both its visitors and its natural features. What's notable, besides quakes, fire is a natural and integral part of the Sierra Nevada ecosystem, playing a critical role in shaping the park's forests, meadows, and wildlife habitats. One of the earliest recorded significant fires in Yosemite was the Big Burn of 1889. This fire consumed approximately 20,000 acres of forest land. At the time, fire management practices were rudimentary, and the primary approach was suppression. The Big Burn highlighted the need for more effective fire control measures. The aftermath of this fire led to increased awareness about the role of fire in forest ecology and the necessity for improved firefighting techniques. Besides Big Burn, the Hetch Hetchy Fire of 1937 was another pivotal event in Yosemite's fire history. This fire burned around 9,000 acres in the Hetch Hetchy Valley, an area already controversial due to the construction of the O'Shaughnessy Dam and the flooding of the valley to create a reservoir. The fire's impact on the landscape and the subsequent soil erosion issues further fueled debates about the environmental management of the valley. This event also underscored the challenges of balancing natural resource management with conservation efforts. Fast forward to 1961, the Harlow Fire burned nearly 44,000 acres, including parts of Yosemite National Park and the surrounding Sierra National Forest. The Harlow Fire was one of the largest wildfires in the region at the time. Its extensive damage prompted a re-evaluation of fire suppression strategies. This fire, along with others during that era, played a role in shifting the National Park Service's policies towards recognizing the ecological benefits of natural fires. The Ackerson Fire of 1977 was also a significant fire that burned approximately 4,150 acres near the park's western boundary. This fire occurred during a period of changing attitudes toward fire management in the United States. The National Park Service had begun to recognize the importance of fire in maintaining healthy forest ecosystems. The Ackerson Fire served as a case study in the emerging practice of letting some naturally ignited fires burn under controlled conditions to achieve ecological benefits. And although not within Yosemite itself, the massive fires that swept through Yellowstone National Park in 1988 had a profound impact on fire management policies across the National Park Service, including Yosemite. The Yellowstone fires burned nearly 800,000 acres, and their severity and scale highlighted the limitations of traditional fire suppression strategies. These fires led to increased acceptance of fire as a natural and necessary part of many ecosystems, including Yosemite's. The events of 1988 accelerated the adoption of policies that allowed for more natural fire regimes in national parks. The A-Rock Fire of 1990 was a significant event in Yosemite's recent history, burning around 17,000 acres. This fire threatened the iconic Yosemite Valley and led to evacuations and extensive firefighting efforts. The A-Rock Fire underscored the ongoing challenge of managing fire in a landscape with both high ecological value and significant human infrastructure. It also highlighted the need for more sophisticated fire management strategies that balance suppression with ecological health. The Rim Fire of 2013 was one of the largest and most destructive fires in Yosemite's history, burning over 257,000 acres, including 77,000 acres within the park's boundaries. The fire, which started outside the park due to a hunter's illegal campfire, spread rapidly due to dry conditions and strong winds. The rimfire caused extensive damage to forests, watersheds, and wildlife habitats. It also had significant economic impacts, including costs related to firefighting, rehabilitation, and loss of tourism revenue. The rimfire served as a stark reminder of the increasing intensity and frequency of wildfires in the context of climate change. The fire's aftermath involved massive rehabilitation efforts, including reseeding, erosion control, and habitat restoration. The rimfire also prompted discussions about forest management practices, including the role of prescribed burns and mechanical thinning to reduce fuel loads and mitigate the risk of future large-scale fires. In the following years, several significant fires have shaped Yosemite's landscape. Especially in 2024, Yosemite National Park faced a series of devastating wildfires that left a profound impact on the landscape, ecology, and community. These fires were some of the most significant in the park's recent history, highlighting the challenges of climate change, forest management, and the resilience of natural ecosystems. The fires began in late June, triggered by an unusually dry winter, followed by a record-breaking heat wave. The dry conditions and high temperatures created the perfect environment for fires to ignite and spread rapidly. Lightning strikes during a summer storm ignited several small fires, which quickly merged into larger infernos. The largest of these, named the Yosemite Complex Fire, spread across thousands of acres within days. Those fires had a catastrophic impact on Yosemite's diverse ecosystems. The intense heat and fast-moving flames devastated large areas of forest, including ancient sequoias, pine forests, and mixed conifer stands. While many animals could flee, slower-moving species and those with limited mobility, such as reptiles and amphibians, suffered significant losses. The fires also altered the landscape dramatically. The once lush and green valleys and mountainsides were transformed into charred remnants. Soil erosion became a significant concern, as the loss of vegetation left the ground vulnerable to heavy rains, which often follow the fire season in California. The human toll of the 2024 fires was significant. Thousands of residents in surrounding communities were evacuated, and many homes and structures were lost. The park itself was closed to visitors for several months, impacting tourism, a vital source of revenue for the local economy. The closure also disrupted the lives of those who work in and around the park, from park rangers and scientists to hospitality workers. Firefighting efforts were monumental. Thousands of firefighters from across the country were deployed to combat the blazes. They used a combination of ground and aerial tactics, including water and fire retardant drops, to contain the fire's spread. Despite their efforts, the fire's intensity and the challenging terrain made it a difficult battle. Now, having said that, the 2024 fires in Yosemite Park provided several critical lessons. First, they reinforced the importance of proactive fire management strategies, including controlled burns and fuel reduction. The nature of wildfires has changed significantly due to human activities. Decades of fire suppression policies have led to an accumulation of fuel in forests, making fires more intense when they do occur. Thus, incorporating traditional ecological knowledge into modern fire management practices is needed. Indigenous-led controlled burns and other traditional land management techniques are being considered more seriously as effective tools for reducing the risk of catastrophic fires. In addition, the 2024 fires in Yosemite National Park were a stark reminder of the challenges posed by climate change. Global climate change is not a future problem. Changes to Earth's climate driven by increased human emissions of heat-trapping greenhouse gases are already having widespread effects on the environment. As temperatures continue to rise and weather patterns become more extreme, the risk of severe wildfires will only increase. This reality presents significant challenges for fire management, conservation, and public safety. Future strategies will need to focus on building resilience in both natural and human communities. This includes improving forest management practices, enhancing early warning systems, and promoting community preparedness. Additionally, addressing the root causes of climate change by reducing greenhouse gas emissions is essential to mitigate the long-term risk of wildfires. What's notable, Yosemite isn't the only national park being closed. Yellowstone, the first national park in the world, also suffered the same fate. Known as a wonder of nature, Yellowstone National Park is globally appreciated for its untamed beauty, with a series of the most active, diverse, and intact collections of combined geothermal features, with over 10,000 hydrothermal sites and half the world's active geysers. Visited by millions each year, tourists travel from all over the world to witness its unique environment. However, while enjoying Wonderland, visitors should also keep safety in mind. Because in fact, there are many ways to get injured or even die while visiting Yellowstone National Park. As reported in the book Death in Yellowstone, there have been numerous causes of death throughout the region's history, including violent confrontations between people, wagon accidents, falling trees, poisonous gases, drownings, falling into hot springs, and, of course, encounters with wildlife. Even in the past few years, news stories have reported bison, gorings, tossings, bear attacks, and fatal falls from selfie moments gone awry. However, contrary to common belief, one of Yellowstone's biggest dangers to the public is not the abundant and diverse wildlife that millions gather to see, nor even human error, such as falls or traffic accidents. It's nature. Lurking beneath Yellowstone National Park is a reservoir of hot magma 5 miles deep, fed by a gigantic plume of molten rock welling up from hundreds of miles below. That heat is responsible for many of the park's famous geysers and hot springs. And as magma rises up into the chamber and cools, the ground above periodically rises and falls. On rare occasions throughout history, that magma chamber has erupted. The vast majority of those eruptions in Yellowstone have been smaller lava flows, with the last occurring at Pitchstone Plateau some 70,000 years ago. But the reason why Yellowstone gets so much attention is the remote possibility of catastrophic super eruptions. A super eruption is anything that measures magnitude 8 or more on the volcano explosivity index, in which at least 240 cubic miles of material gets ejected. That's enough to bury Texas 5 feet deep. These super eruptions are thousands of times more powerful than even the biggest eruptions we're used to. Here's a chart from USGS comparing the Yellowstone super eruptions with the Mount St. Helens eruption of 1980. The difference is staggering. Yellowstone has had 3 of these really massive eruptions in its history: 2.1 million years ago, 1.3 million years ago, and 664,000 years ago. Each of the previous eruptions spewed enormous amounts of volcanic ash, gas, magma, and other volcanic debris that covered most of the continental US. Some material has been found as far away as Louisiana. After each of these eruptions, the Yellowstone supervolcano collapsed on itself, sucking in trees, mountains, and everything else in the landscape. The depression formed by this phenomenon is called a caldera. A caldera-forming eruption would create a massive natural hazard in Yellowstone. Scientists say the last Yellowstone eruption was 1,000 times greater than the notorious 1980 Mount St. Helens eruption that killed 56 people and thousands of animals, and scorched hundreds of square kilometers of land in Washington and Oregon. Thousands of years ago, the last blast from the Yellowstone supervolcano shot a fatal plume of hot ash, molten rock, and lethal gases thousands of meters into the air. A third of the continent was likely plunged into complete darkness. Pyroclastic flows, fast-moving currents of hot, dry rock fragments and gases, raced along the region at alarming speeds, burying or shattering anything in their path. Magma spewing out of the ground charred the once charming landscape for kilometers. Some evidence of the last eruption can be found in the Yellowstone caldera itself, 30 miles wide and 45 miles long. The thick volcanic debris that remained after the eruption can still be seen in an area referred to as the Lava Creek Tuff. How terrifying. That raises the question, what would happen if a supervolcano eruption occurred again at Yellowstone? Frankly, its effects would be worldwide. The main damage would come from volcanic ash, a combination of splintered rock and glass that was ejected miles into the air and scattered around the country. A super eruption could conceivably bury the northern Rockies in 3 feet of ash, devastating large swaths of Wyoming, Idaho, Colorado, Montana, and Utah. Meanwhile, the Midwest would get a few inches of ash, while both coasts would see even smaller amounts. The exact distribution would depend on the time of year and weather patterns. Regardless, any of those scenarios would be terrible news. That much volcanic ash is capable of killing people, plants, and animals, and crushing buildings. Even a few inches of ash, which is what much of the country can get, can destroy farms, clog roadways, cause serious respiratory problems, block sewer lines, and even short out transformers. Air travel would have to shut down across much of North America. A volcanic eruption that big would also have major effects on the global climate. Volcanoes can emit sulfur aerosols that reflect sunlight back into the atmosphere, cool the climate. These particles are short-lived in the atmosphere, so the effect is only temporary, but it can still be dramatic. When Pinatubo erupted in 1991, it cooled the planet by about verdigris for a few years. The Tambora eruption in 1815 cooled the planet enough to damage crops around the world, possibly leading to famines in some areas. And those were relatively tiny eruptions compared to what a supervolcano is, in theory, capable of. Obviously, once supervolcano eruption occurred again at Yellowstone, that means doomsday is coming. Luckily, NASA has a plan to stop it. They found that the most logical solution could simply be to cool a supervolcano down. A volcano the size of Yellowstone is essentially a gigantic heat generator equivalent to 6 industrial power plants. Yellowstone currently leaks about 60–70% of the heat coming up from below into the atmosphere via water, which seeps into the magma chamber through cracks. The remainder builds up inside the magma, enabling it to dissolve more and more volatile gases and surrounding rocks. Once this heat reaches a certain threshold, then an explosive eruption is inevitable. But if more of the heat could be extracted, then the supervolcano would never erupt. NASA estimates that if a 35% increase in heat transfer could be achieved from its magma chamber, Yellowstone would no longer pose a threat. The only question is how. One possibility is to simply increase the amount of water in the supervolcano. But from a practical perspective, it would likely be impossible to convince politicians to sanction such an initiative. According to Brian Wilcox of NASA's Jet Propulsion Laboratory, JPL, at the California Institute of Technology, building a big aqueduct uphill into a mountainous region would be both costly and difficult, and people don't want their water spent that way. People are desperate for water all over the world, and so a major infrastructure project where the only way the water is used is to cool down a supervolcano would be very controversial. Instead, NASA has conceived a very different plan. They believe the most viable solution could be to drill up to 10 kilometers down into the supervolcano and pump down water at high pressure. The circulating water would return at a temperature of around 350 C, thus slowly day by day extracting heat from the volcano. And while such a project would come at an estimated cost of around $3.46 BN, it comes with an enticing catch, which could convince politicians to make the investment. In the words of Wilcox, Yellowstone currently leaks around 6 GW in heat. Through drilling in this way, it could be used to create a geothermal plant, which generates electric power at extremely competitive prices of around 0.10 camol. You would have to give the geothermal companies incentives to drill somewhat deeper and use hotter water than they usually would, but you would pay back your initial investment and get electricity, which can power the surrounding area for a period of potentially tens of thousands of years. And the long-term benefit is that you prevent a future supervolcano eruption, which would devastate humanity. But drilling into a supervolcano does not come without certain risks, namely triggering the eruption you're intending to prevent. The most important thing with this is to do no harm, Wilcox says. If you drill into the top of the magma chamber and try and cool it from there, this would be very risky. This could make the cap over the magma chamber more brittle and prone to fracture. And you might trigger the release of harmful volatile gases in the magma at the top of the chamber, which would otherwise not be released. Instead, the idea is to drill in from the supervolcano from the lower sides, starting outside the boundaries of Yellowstone National Park, and extracting the heat from the underside of the magma chamber. This way, you're preventing the heat coming up from below from ever reaching the top of the chamber, which is where the real threat arises. However, those who instigate such a project will never see it to completion, or even have an idea whether it might be successful within their lifetime. Cooling Yellowstone in this manner would happen at a rate of 1 meter a year, taking of the order of tens of thousands of years until just cold rock was left. Although Yellowstone's magma chamber would not need to be frozen solid to reach the point where it no longer posed a threat, there would be no guarantee that the endeavor would ultimately be successful for at least hundreds and possibly thousands of years. But to prevent a catastrophe, such long-term thinking and planning may be the only choice. With a project like this, you'd start the process, and the main ongoing benefit you'd see in everyday terms is this new supply of electrical power, Wilcox says. Such a plan could be potentially applied to every active supervolcano on the planet, and NASA's scientists are hoping that their blueprints will encourage more practical scientific discussion and debate for tackling the threat. As Wilcox said, when people first considered the idea of defending the Earth from an asteroid impact, they reacted in a similar way to the supervolcano threat. People thought, as puny as we are, how can humans possibly prevent an asteroid from hitting the Earth? Well, it turns out, if you engineer something which pushes very slightly for a very long time, you can make the asteroid miss the Earth. So, the problem turns out to be easier than people think. In both cases, it requires the scientific community to invest brain power, and you have to start early. But Yellowstone explodes roughly every 600,000 years, and it is about 600,000 years since it last exploded, which should cause us to sit up and take notice. That's all the information that we have for you today. Don't forget to give us a thumbs up if you enjoyed today's episode, subscribe if you haven't already, and hit the bell so you never miss out on future episodes. And be sure to also tell us what you think about today's content. Everyone's support motivates us to continue delivering quality content and to always improve. As always, thanks for watching, and we will see you next time.